For weeks, these sharp images have remained hidden from view, locked away in NASA's servers, the sharpest images ever taken of something that shouldn't even exist in our solar system, an object that came from a place we've never touched, orbiting a star we've never named, images so detailed they could rewrite what we thought we knew about visitors from deep space. And yet, you haven't seen them. Neither have the scientists who've dedicated their careers to moments like this. Neither has anyone outside a handful of people behind closed government doors. These aren't just photographs. They're the closest look humanity has ever gotten at an interstellar traveller, captured by a camera designed to spot details smaller than a car from Martian orbit, now turned toward a comet that crossed the boundary between star systems and entered ours. NASA's Mars Reconnaissance Orbiter photographed Comet 3I Atlas during its closest approach to Mars in early October. The timing was perfect, the angle was ideal, the technology was ready, everything aligned for what should have been an immediate scientific breakthrough shared with the world. But then something happened. The United States government shut down, and in the silence that followed, while other nations released their observations and ground telescopes, continued tracking the comet's path, NASA's most valuable data remained sealed. The shutdown has ended, operations have resumed, budgets are being discussed again. Yet those images, the ones that could answer whether this interstellar visitor survived its journey around the Sun, whether its core remained intact, whether everything we've theorized about objects from beyond our solar neighborhood holds true, still haven't been released to the public until now. Sources inside the agency confirm that NASA is preparing to make the HiRISE images of 3I Atlas available as early as next week. Not estimates, not artist renderings, actual photographs captured at a resolution 3 times sharper than anything the Hubble Space Telescope achieved when it observed this same object months ago. These images will show structures we've only guessed at. They'll reveal details that could settle debates raging in the scientific community since summer. They might even show us the nucleus itself, the frozen heart of a comet born in another star's shadow. But here's what nobody's talking about yet. The delay wasn't just bureaucratic inconvenience. It took congressional intervention to force this release, a formal letter from a member of the House of Representatives demanding transparency, accountability, and immediate access to data that, by all reasonable standards, should have been public weeks ago. The letter didn't just ask for the Mars images. It demanded supplementary observations from every NASA mission that pointed instruments toward this comet. It asked why the American public, whose tax dollars built these spacecraft and cameras, had been kept in the dark, while the object they were sent to study passed the most critical phase of its journey through our solar system that raises uncomfortable questions. What happens when the most transparent space agency in history suddenly goes quiet at the exact moment the world is watching? What does it mean when scientists trained to share discoveries immediately find themselves waiting behind institutional barriers they can't see or understand? And what will we actually see when those images finally go public? Not just about the comet, but about the process that kept them hidden. This isn't conspiracy. This isn't speculation about what might be lurking in those photographs. This is about something more fundamental. The tension between public curiosity and governmental control. The friction that emerges when groundbreaking discoveries collide with bureaucratic procedures, and the growing frustration of a scientific community that knows the data exists but can't access it. Because while we've been waiting, 3I Atlas hasn't stopped moving. It swung around the Sun at its closest point in late October, enduring temperatures and radiation that tear some comets apart. Ground observations from November suggest it survived. Its tail is still visible, still growing, still producing the signature glow of active outgassing. But survival doesn't mean intact. Comets can fragment into pieces and still appear functional from Earth's distant vantage point. The HiRISE images were captured before that critical solar passage. They show the comet as it was, whole, active, under stress but not yet tested by the Sun's full intensity. Combined with observations from the weeks that followed, they could tell us whether this visitor held together or quietly broke apart when no one was close enough to watch. That's not a minor detail. That's the difference between understanding these objects as resilient wanderers or fragile refugees barely holding their structure as they drift between stars. So if you've been following this story since the comet first appeared in our skies, if you've wondered why an object from interstellar space matters enough to command this much attention, or if you're just now realizing that something unprecedented is about to unfold, stay with me. What's coming could reshape how we see our place in a galaxy filled with travelers we're only beginning to notice. October was the month that mattered. Not because the comet was at its brightest or closest to Earth. It wasn't. October mattered because 3. HiAtlas passed within striking distance of Mars, and Mars happens to be the most heavily instrumented planet beyond our own. Think about that for a moment. An object from another star system, something that formed billions of years ago in conditions we can only imagine, travelling through the cold darkness of space for longer than human civilization has existed, happened to pass close enough to the red planet that every spacecraft we've stationed there could turn and look, and they did. Europe's Mars Express orbiter observed it. The ExoMars Trace gas orbiter pointed its spectrometers toward the comet, breaking down its light into wavelengths that reveal chemical signatures, the fingerprints of molecules like carbon dioxide, water vapor, and compounds we're still identifying. China's Tianwen-1 probe captured images that would later become the first publicly released visuals from Mars orbit, grainy but unmistakable proof that something from beyond our solar neighbourhood had crossed into view. But none of those instruments compared to what NASA had waiting. The HiRISE camera wasn't designed for this. It was built to photograph Martian geology, craters, canyons, dust devils, and the subtle patterns left by ancient water mission planners. Use it to scout landing sites for rovers, to study how ice deposits change with the seasons, to watch avalanches cascade down cliff faces in real time. Its resolution is absurd by spacecraft standards. From Martian orbit, it can resolve features smaller than a dining table. When engineers designed it, they were thinking about rocks and sand dunes, not comets from interstellar space. But engineering excellence has a way of exceeding its original purpose, and when the opportunity arose to point HiRISE at 3i Atlas during its closest approach, the team didn't hesitate. The geometry was almost perfect. The comet's trajectory brought it within 19 million miles of Mars, close enough that HiRISE could capture details invisible to Earth-based telescopes, close enough that the resolution advantage over Hubble became undeniable. Hubble had observed this same object months earlier, producing stunning images that helped scientists estimate size and track activity. But Hubble operates from Earth orbit, looking across tens of millions of miles of space at a target moving fast and glowing faintly. Distance blurs details. Atmosphere, even the thin wisp that Hubble orbits above, scatters light. HiRISE had proximity, it had clarity, and it had multiple opportunities, capturing images over several days as the comet moved through its closest approach. That's where the story gets interesting. Because this wasn't a single snapshot. HiRISE photographed 3i Atlas repeatedly, watching how its appearance changed over time. Did the jets of gas and dust shift position as the comet rotated? Did the coma, the glowing cloud surrounding the nucleus, expand or contract as solar radiation increased? Were there sudden bursts of activity, or did the outgassing remain steady? These aren't abstract questions. They reveal how the comet is structured, how it responds to heat, and whether its rotation is stable or chaotic. For an object we'll never visit, never sample, never touch with human hands, this kind of time-lapse observation is as close as we get to understanding its nature. And then there's the question everyone's been asking since October. Did HiRISE see the nucleus? Not the coma, not the tail, not the glowing haze of sublimating ice, the actual solid core of the comet itself. Most estimates put the nucleus somewhere between a few hundred meters and maybe a couple of kilometers across. That's small. Small enough that even from Martian orbit, even with HiRISE's resolution, it might be nothing more than a bright point of light buried inside the surrounding glow. But if the activity was moderate, if the dust production wasn't overwhelming, if the geometry aligned just right, there's a real possibility that the nucleus is visible as a distinct feature in those images. If that's true, scientists won't need to estimate size anymore. They'll measure it directly. They'll see its shape, whether it's spherical, elongated, irregular. They might even detect surface features, though that's pushing the limits of what's physically possible, given the distance and the comet's size. But even a clear measurement of brightness and position would be transformative. It would anchor every other observation. It would give us a baseline to compare against the comet's appearance before and after its closest approach to the Sun, letting researchers track how much mass it lost, how its activity evolved, whether its structure held or fractured under thermal stress. This is why the Mars flyby mattered. This is why scientists have been waiting with a kind of restless urgency that doesn't usually characterize their work, because Opportunities like this don't come around often. Interstellar objects are rare. We've only confirmed a handful in the entire history of astronomy. Most pass through the inner solar system too quickly for detailed study. By the time we notice them, they're already leaving. But 3i Atlas was different. It was discovered early enough that telescopes had time to prepare, missions had time to coordinate, and spacecraft already stationed around other planets had time to adjust their pointing and capture data that would have been impossible from Earth. The HiRISE images represent the best chance we've had, and possibly the best chance we'll have for years, to see an interstellar comet at high resolution. They're not just pretty pictures. They're scientific evidence captured at a critical moment, preserved in digital form, waiting to be analysed by researchers who've spent careers preparing for exactly this kind of event. And they've been waiting, locked behind the procedural walls of a government agency that went dark at the worst possible time. Timing is everything. And in the case of 3i Atlas, the timing felt almost cruelly ironic. The Mars flyby concluded in early October. Data streamed back to Earth, processed by systems designed to handle the flood of information pouring down from spacecraft scattered across the solar system. Scientists tracking the comet expected updates within days. NASA's standard procedure for high-priority observations is transparency. Raw data gets released to researchers, findings get shared, the public gets briefed. It's a system that's worked for decades, a rhythm the space community relies on. But early October brought something unexpected. The United States government shut down. Not because of a crisis, not because of emergency, but because of the kind of budgetary impasse that periodically paralyzes federal operations. Agencies switched to skeleton crews. Non-essential functions ceased. Websites froze mid-update. And NASA, an institution that prides itself on being a beacon of scientific openness, went quiet just as the most detailed images of an interstellar object were landing on their servers. The shutdown affected everything. Planetary missions continued operating. You can't just turn off a spacecraft millions of miles away. But public communication stopped, data releases halted. Press briefings were cancelled. Scientists who'd coordinated observations with NASA missions found themselves cut off from the information they needed to do their work. For weeks, the only updates on 3i Atlas came from observatories outside the United States. Ground-based telescopes in the southern hemisphere tracked the comet. As it continued toward the Sun, China released images from Tianwen-1, low resolution but at least visible, at least something. Europe's orbiters shared spectroscopic data, but NASA's HiRISE images, the ones everyone was waiting for, remained inaccessible. Days turned into weeks. The comet reached perihelion in late October, the closest point in its orbit to the Sun, the moment of maximum danger when heat and radiation can shatter a comet's nucleus or strip away its outer layers entirely. Ground observations after perihelion showed the comet still active, still producing a visible tail, still outgassing as it climbed back outward. That was encouraging. It suggested the nucleus had survived. But survival isn't the same as staying intact. Comets can break into fragments and still look active from Earth. The pieces continue releasing gas and dust. The tail persists. From our distant perspective, nothing appears wrong until detailed observations reveal the fracture. The HiRISE images, captured before perihelion, represented a critical baseline. They showed the comet in its pre-solar encounter state. Combined with post-perihelion observations, they could reveal whether the nucleus maintained its structure, or whether subtle changes hinted at fragmentation. But accessing those images required NASA to release them. And as October became November, as the shutdown officially ended and government operations resumed, the images still didn't appear. That's when frustration turned into something sharper. Scientists aren't typically confrontational. They work within systems, navigate bureaucracies, wait for approvals. But the silence around the HiRISE data was unusual, even by the slow standards of institutional science. Other missions had resumed data releases. Other observations were being shared. Yet the most valuable dataset from the most significant interstellar event in years remained locked away, and no one could explain why. The scientific community started asking questions publicly. Why the continued delay? Was there a technical problem with the images? Had something gone wrong during observation or processing? Or was this purely administrative, a backlog created by the shutdown, now compounded by an abundance of caution about releasing information that had generated significant public attention? The answers weren't forthcoming, NASA's public affairs offices, still recovering from the shutdown, offered no timeline. The HiRISE team, bound by agency protocols, couldn't release data without approval, and so the waiting continued. Then, on the last day of October, something shifted. Congresswoman Anna Paulina Luna sent a formal letter to NASA's acting administrator. It wasn't a polite inquiry, it was a demand. Release the HiRISE imagery immediately. Provide supplementary data from every NASA mission that observed the comet. Explain any unusual readings from instruments near Mars during the flyby share, observations from the Parker Solar Probe, from the James Webb Space Telescope, from any spacecraft that might have captured relevant information. Make it public. Make it transparent. Make it available to the researchers who've been asking for weeks, and the public who funded the missions that captured this data. The letter went further. It called for the release of unrelated interstellar data that NASA had been holding, meteor impact records, trajectory analyses, anything that might help scientists understand the population of objects crossing into our solar system from interstellar space. By broadening the scope, Luna was making a larger point. This isn't just about one comet. This is about a pattern of delays, of reviews that stretch beyond reason, of data sitting in government databases while the scientific community that needs it waits on the outside. Her letter wasn't just read by NASA officials, it went public. News outlets covered it. Astronomy forums discussed it. Social media lit up with reactions ranging from support to skepticism about governmental transparency. Suddenly, what had been a niche concern among researchers became a mainstream story. Why was NASA withholding the sharpest images ever taken of an interstellar visitor? What justified the delay? And what would it take to finally see what had been captured during those critical days in October? The pressure mounted, and behind the scenes, according to sources familiar with the agency's internal processes, reviews accelerated. Not because the data was problematic, there's no indication the images failed or revealed something unexplainable, but because the institutional calculus had changed. Transparency wasn't optional anymore. It was expected, demanded, and overdue. The images existed. They'd been processed. And now, finally, they were being prepared for release. So what happens when those images finally go live? What are we actually looking at? And why does it matter beyond the immediate thrill of seeing something no one's seen before? Understanding that requires stepping back from the specifics of this comet and thinking about what interstellar objects represent. They're not just anomalies passing through, they're messengers from environments we can't visit, carrying information encoded in their structure, their composition, their behavior. Every detail we can capture teaches us something about the kinds of worlds that form around other stars, the chemistry that exists in those distant systems, the processes that eject objects into the space between stars. The HiRISE images will show us the comet as it appeared during its closest approach to Mars, active, glowing, surrounded by the coma of gas and dust that's been visible since summer. But the quality of those images, the resolution, the clarity, that's what changes everything. When Hubble observed 3I Atlas earlier, it captured the comet's overall appearance, the shape of its coma, the asymmetry of its jets. Those observations were valuable. They gave scientists a sense of scale, a rough estimate of the nucleus size based on brightness, and evidence that the comet's outgassing wasn't uniform. Some regions were more active than others, suggesting the nucleus was rotating, and that certain areas faced the sun at different times, heating up and releasing gas in bursts. HiRISE should see those jets in far greater detail. If the images are as sharp as expected, we might see the individual streams as they leave the surface, the way material spreads outward as it escapes the comet's weak gravity, the geometry of the coma as it evolves over hours and days. That's not just visually impressive, it's scientifically critical. The pattern of jets reveals where the active regions are located. It tells us about the comet's rotation period, its axis of spin, and whether the activity is stable or changing as the comet heats up. For an object we'll never study up close with a dedicated mission, this kind of observational data is everything. And then there's the nucleus itself. This is the question that's been driving speculation since October. Did HiRISE resolve the nucleus as a distinct object, or is it buried too deeply inside the coma to separate from the glow? Most comets observed from spacecraft show nuclei that are dark, irregularly shaped, and covered in dust. They're not bright. They don't shine on their own. They're only visible because sunlight reflects off their surfaces, and even then, they're difficult to distinguish from the material streaming off them. But HiRISE captured multiple images over several days. If the activity varied, if there were moments when the outgassing decreased or shifted direction, there might be frames where the nucleus is more exposed, more visible, more clearly defined against the surrounding glow. If that's the case, if even one image shows the nucleus as a distinct point or shape, scientists will finally have direct confirmation of its size. Not an estimate based on brightness models, not a guess derived from how much gas the comet produces, an actual measurement based on visible features. That measurement cascades into everything else. It lets researchers calculate the nucleus's mass more accurately. It constrains models of how much material the comet has lost since becoming active. It provides context for understanding whether this object is typical of interstellar comets or an outlier in the population. There's also the survival question. Ground-based observations from mid-November show that 3I Atlas is still producing a tail, still outgassing, still visibly active. That's strong evidence it didn't disintegrate during perihelion. But activity alone doesn't confirm the nucleus remained intact. Comets can fragment into multiple pieces and still appear as a single glowing object from Earth. The fragments continue releasing gas. They move along similar trajectories. From a distance, the comet looks whole even if its nucleus is quietly split apart. The HiRISE images, captured before perihelion, give us a pre-encounter baseline. When scientists compare those early images to observations made after the Sun passage, they'll be looking for changes. Did the brightness increase or decrease? Did the coma expand or contract? Did new jets appear, or did old ones fade? Those changes can reveal whether the nucleus lost mass, whether surface layers eroded, whether structural weaknesses developed that might lead to fragmentation later. Comets don't break apart instantly. The process can take weeks or months as thermal stress works through the ice and rock, exploiting fissures, widening cracks, until pieces finally separate. So far, there's no confirmed evidence that 3I Atlas has fragmented. But the HiRISE data, once analysed, will provide the clearest picture we have of the comet's condition at a critical moment. That clarity matters because interstellar comets are rare. We don't have a large sample to study. Every observation, every measurement, every detail we can extract becomes part of the foundation for understanding these objects as a class. Are they fragile wanderers barely holding together as they drift between stars? Or are they resilient survivors, their nuclei strong enough to endure thermal shocks, gravitational tugs, and the violence of close solar approaches? The answer affects how we interpret detections of future interstellar visitors. It shapes mission planning for spacecraft designed to intercept and study these objects up close. It informs models of how common interstellar comets are, how many might be passing through our solar system undetected, and what kinds of instruments we need to characterize them effectively. The HiRISE images of 3I Atlas won't answer all those questions. No single dataset ever does. But they'll narrow the possibilities. They'll give us constraints. They'll show us what one interstellar comet looked like at a moment of stress, captured with a clarity we've never had before. And that clarity is about to become public. Next week, maybe sooner, those images will appear on NASA's servers. Researchers will download them within minutes. Analysis will begin immediately, spreading across institutions and continents as scientists compare notes, run models, and extract every possible measurement from the data. The rest of us will see the images too, raw or processed, annotated or plain, depending on how NASA chooses to present them, but we'll see them finally. And the waiting, the frustration, the questions about why it took so long, all of that will shift into the background as the focus moves where it belongs, to the science, the discovery, the quiet thrill of seeing something that came from another star. There's a moment in every bureaucratic delay when patience stops being a virtue and starts feeling like complicity. For scientists tracking 3I Atlas, that moment arrived in late October when the government shutdown ended, operations resumed, and the HiRISE images still didn't appear. The reasons offered, internal reviews, processing backlogs, standard protocols, sounded reasonable in isolation. But taken together, stretched across weeks, they began to feel less like explanations and more like excuses because the data existed. The images had been captured, transmitted, and stored. The technical work was done. What remained was a decision: share the information or keep it internal. Congresswoman Luna's letter forced that decision into the open. Her October communication to NASA's acting administrator wasn't framed as a request. It was a demand for transparency, grounded in the principle that publicly funded research belongs, in some fundamental sense, to the public. The letter outlined specific asks: release the HiRISE imagery, provide data from supplementary observations by other NASA missions, explain any anomalous readings detected during the Mars flyby. But beneath those specifics was a broader challenge to the agency's handling of information that should have been accessible weeks earlier. What made the letter particularly effective wasn't just its directness, it was the scope. Luna didn't limit her demand to the Mars images she called for transparency around other interstellar data that NASA had been holding: meteor records, trajectory analyses, impact assessments that could help scientists understand how many objects from beyond our solar system pass through undetected. By connecting those requests to the HiRISE delay, she was drawing attention to a pattern. One delayed dataset might be explained as procedural caution. Multiple delays across different missions and observation types start to look like something else. The letter went public almost immediately. That wasn't accidental. By making the request visible, Luna ensured that NASA's response, or lack of one, would be scrutinized beyond the scientific community news outlets picked up the story. Astronomy publications covered it. Forums and social media platforms buzzed with reactions. Some praised the congressional intervention as necessary accountability. Others questioned whether political pressure on scientific institutions was appropriate, even when the goal was transparency. But almost everyone agreed on one thing. The delay had gone on too long, and the lack of clear explanation was eroding trust. Trust is fragile in science. It's built through consistent openness, through sharing data before conclusions are fully formed, through letting the global research community participate in analysis, rather than hoarding information until internal reviews are complete. NASA has historically excelled at this. From the Apollo missions to the Mars rovers to the James Webb Space Telescope, the agency's default posture has been transparency. Raw images appear online within hours of being captured. Data gets released to researchers worldwide. Discoveries are announced in press conferences where scientists explain not just what they found, but how they found it and what uncertainties remain. That's the standard. That's what the scientific community expects. And when the HiRISE images didn't appear, when weeks passed without explanation, it felt like a departure from that standard. Not because anyone suspected NASA was hiding something extraordinary. There's no credible reason to think the images show anything other than a comet behaving like a comet. But because the delay itself, the opacity around decision-making, the absence of a clear timeline, all of it ran counter to the agency's stated values. Luna's letter reframed the issue. It wasn't just about one comet or one dataset. It was about whether transparency would remain the norm or become conditional, applied selectively based on factors the public couldn't see or evaluate. By demanding immediate release and attaching congressional oversight to that demand, she was asserting that the default should always be openness, unless there's a compelling, articulable reason to delay. Procedural backlog doesn't qualify. Internal caution doesn't justify weeks of silence. If the data is ready, if the images are processed, if the information is scientifically valuable, it should be public. The response from NASA, when it came, was measured. Officials acknowledged the request, confirmed that the HiRISE images were being prepared for release, and indicated that supplementary data would be made available as processing allowed. There was no dramatic announcement, no admission of wrongdoing, no suggestion that the delay had been anything other than standard procedure complicated by the shutdown, but the timeline accelerated. Reviews that might have stretched into December suddenly concluded. Approvals that had been pending moved forward, and sources inside the agency began confirming what the scientific community had been hoping to hear. The images would be public soon, possibly within days. That shift matters. Not because it validates conspiracy theories or suggests NASA was intentionally withholding information. It matters because it demonstrates that transparency isn't automatic. It requires pressure, advocacy, and sometimes formal intervention from outside the system. Scientists can request data, they can ask questions, they can express frustration in journals and conferences. But when those requests go unanswered, when delays stretch beyond reasonable bounds, external accountability becomes necessary. Luna's letter provided that accountability. It turned a scientific data issue into a transparency issue, and in doing so, It forced the kind of institutional response that internal requests hadn't achieved. The lesson isn't that NASA is secretive or that congressional intervention should be routine. The lesson is that openness requires vigilance. It requires people willing to ask uncomfortable questions, to challenge delays that don't make sense, to insist that public research remain public. The HiRISE images will be released because the system eventually worked. But the fact that it took this long, that it required congressional pressure, suggests the system worked imperfectly. And that's worth remembering the next time important data sits behind institutional barriers while the world waits. Step back from the immediate details, the Mars flyby, the government shutdown, the delayed images, and the deeper significance of 3i Atlas starts to emerge. This isn't just about one comet passing through our solar system. It's about what that comet represents. A sample from an environment we cannot reach, formed under conditions we can only model, carrying information about processes that happened light years away in a region of space we'll never visit with human-made probes. Interstellar objects are scientific couriers. They bring evidence of distant places directly to our doorstep, and every measurement we make adds to our understanding of the galaxy beyond our immediate neighbourhood. Think about how planetary science typically works. We study our own solar system, the planets, moons, asteroids and comets that orbit the Sun, because that's what's accessible. We send spacecraft to Mars, to Jupiter, to Saturn, to the outer edges where icy bodies orbit in the darkness. Every rock sample, every atmospheric reading, every image teaches us about the conditions that existed when our solar system formed. We learn what materials were present, how they combined, how planets grew from dust and gas into the worlds we see today. That knowledge is invaluable, but it's also limited. It's one data point, one star system, one set of initial conditions. Interstellar comets change that. They give us comparative data. When 3i Atlas passed close enough for detailed observation, scientists didn't just see a comet. They saw evidence of a planetary system that formed somewhere else, under different conditions with different chemical abundances. The James Webb Space Telescope analysed the comet's composition and found it unusually rich in carbon dioxide, with lower water content than typical solar system comets. That difference is significant. It suggests the environment where 3i Atlas formed was colder, or had a different ratio of elements available during planet formation. It tells us that not all star systems produce the same kinds of comets, that the building blocks of planets vary depending on where and when they form. Why does that matter? Because understanding the diversity of planetary systems helps us understand how common Earth-like conditions might be. If comets from other stars are chemically similar to ours, it suggests that the processes that led to life on Earth, delivery of water and organic molecules by cometary impacts, could happen elsewhere. If interstellar comets are radically different, it raises questions about whether the same pathways to life exist around other stars. Every interstellar visitor we study adds a data point to that larger question. Are we typical? Are the conditions that allowed life to emerge here common in the galaxy? Or are we an outlier, a lucky combination of factors that rarely align? 3. iAtlas can't answer that question alone. No single comet can. But it contributes. It shows us one example of what forms in another star system. And when we eventually detect more interstellar objects, because we will, as survey telescopes improve, and our ability to spot faint, fast-moving targets increases, we'll be able to compare them. We'll start to see patterns. We'll learn whether carbon dioxide-rich comets like 3i Atlas are common or rare. We'll discover if water-poor compositions are typical of certain stellar environments. We'll build a catalogue of interstellar chemistry, piece by piece, visitor by visitor. That catalogue has practical implications. Missions are being planned right now to intercept and study interstellar objects up close. The European Space Agency's Comet interceptor is designed to launch into space and wait in a parking orbit until a suitable target appears, then dispatch itself to rendezvous with the object for detailed study. That mission won't launch for years, but when it does, the target selection will depend on what we've learned from objects like 3i Atlas. What size nucleus should we prioritize? What activity level indicates a target worth intercepting? What chemical signatures suggest the most scientifically valuable composition? The HiRISE images, once released and analysed, will help answer those questions. They'll show us how an interstellar comet behaves under close observation, how its structure holds up during a solar encounter, how its jets and outgassing evolve as it moves through the inner solar system. That information feeds directly into mission planning. It tells engineers what to expect, what instruments to prioritize, what kind of data will be most valuable when we finally get a spacecraft alongside one of these visitors. There's also a broader philosophical dimension to studying interstellar objects. They remind us that the galaxy is not a collection of isolated islands. It's a dynamic, interconnected environment where matter moves between stars, where the debris of planet formation gets scattered across light years, where objects born in one system can drift for millions of years and arrive in another. We tend to think of the solar system as ours, as bounded and separate, but interstellar comets dissolve that boundary. They show us that we're part of something larger, that the space between stars isn't empty but filled with wanderers, and that occasionally those wanderers pass close enough for us to notice. That realization changes how we think about exploration. We're not just studying our local environment, we're sampling the galaxy. Every interstellar object is a gift, a chance to study material from a place we'll never reach, to analyze chemistry that evolved under different conditions, to test our models of planet formation against evidence from beyond the sun's influence. And the more we learn, the better equipped we become to understand what's out there. How many stars have planetary systems? How many of those systems produce comets and asteroids? How many of those objects get ejected into interstellar space, drifting through the darkness until they encounter another star? The numbers are staggering. Some estimates suggest there could be trillions of interstellar objects in the galaxy. Rogue planets, asteroids, comets, all moving independently, all carrying the history of their formation in their structure and composition. Most will never come near us. Most will remain undetected, invisible, lost in the vastness of space, but a few will pass through. A few will come close enough for our telescopes to spot them, our spacecraft to photograph them, our scientists to study them. 3i Atlas is one of those few, and every measurement we make, every image we capture, every spectrum we analyze adds to the slowly growing body of knowledge about what exists in the spaces between the stars. That's why the HiRISE images matter. Not just because they are sharp or unprecedented, but because they represent our best effort to understand something that came from beyond our reach and gave us the rare opportunity to see it up close. That opportunity won't last. The comet is already moving away, fading as it climbs back out toward the outer solar system. Within months it will be too faint to observe, and then it will be gone, back into the darkness, never to return. But the images will remain, the data will remain, and the knowledge we extract from them will shape how we approach the next interstellar visitor, and the one after that, as we slowly piece together the story of the galaxy beyond our sun. The waiting is almost over. Sources confirm that NASA is finalizing the release of the HiRISE images, with publication expected within days. When those images go live, they'll appear on the Mars Reconnaissance Orbiter mission website, not with fanfare, not with a dramatic press conference, but in the understated way that scientific data typically enters the public domain. There will be technical documentation, calibration notes, explanations of observation geometry. There may be a brief statement from the HiRISE team contextualizing what the images show and what limitations exist in their interpretation, but the images themselves will be the story. Within hours of release, scientists around the world will download them. Researchers at universities, observatories, and space agencies will open the files, run initial analyses, and begin extracting measurements. They'll look for the nucleus, for signs of jets, for asymmetries in the coma that reveal rotation and active regions. They'll compare the Mars observations to earlier data from Hubble, from Webb, from ground-based telescopes. They'll build timelines showing how the comet's appearance changed as it moved through the inner solar system. And they'll start writing papers, peer-reviewed studies that will take months to complete, but will form the foundation of our understanding of this object. That process is how science works. Not through instant revelation, but through slow, careful accumulation of evidence. The HiRISE images won't answer every question, they'll raise new ones. They'll reveal details that don't fit existing models, that require new explanations, that push researchers to refine their theories. That's progress. That's how knowledge advances, not in leaps, but in steps, each observation building on the last, each measurement constraining possibilities, each dataset narrowing the range of what's plausible. For those of us outside the research community, the release will offer something different. We'll see the images, we'll read the explanations, we'll get a glimpse of what an interstellar visitor looks like when observed with the best tools humanity has placed around another planet. that glimpse matters. It connects us to a story that's been unfolding for months, that started when 3I Atlas was first detected and will continue as long as the comet remains observable. We'll see the culmination of engineering that put a camera in Martian orbit, of planning that redirected that camera toward a target millions of miles away, of coordination between scientists across continents who worked to ensure no opportunity was missed. But the release isn't the end. 3. Our Atlas is still visible from the southern hemisphere, still producing a tail, still moving outward from the Sun. Ground-based telescopes continue tracking it. Observations are scheduled through December and into early next year. Each observation adds data, brightness measurements, spectroscopic analysis, positional tracking that refines our understanding of the comet's trajectory. By combining all of those observations with the HiRISE images, researchers will build the most complete portrait we've ever had of an interstellar object's journey through our solar system. There's also the question of follow-up missions. The European Space Agency's Comet interceptor, still in development, represents the next step in interstellar object research. It's designed to be a rapid response mission, launched into a holding orbit and dispatched to intercept a newly discovered target. When it eventually flies, the data from 3I Atlas will inform its design, its instruments, its science objectives. What did we learn from observing this comet that tells us what to prioritize next time? What measurements were we unable to make that a dedicated mission could achieve? What questions remain unanswered that can only be resolved by getting close, by sampling the coma, by photographing the nucleus at resolutions HiRISE could never achieve from Martian orbit? Those questions drive the future. They ensure that 3I Atlas, even after it fades from view, will continue influencing how we study interstellar visitors. Every comet that follows will be compared to this one. Every observation will be measured against the benchmark set by the HiRISE images and the coordinated campaign that track this object from discovery through perihelion and beyond. We'll get better at this. We'll detect interstellar objects earlier, observe them more comprehensively, extract more information from each encounter, and eventually we'll send a mission to one. Not just to observe from a distance, but to travel alongside, to study it up close, to answer questions that remote sensing can never fully resolve. The future feels closer because of 3I Atlas. Not because this comet is unique, but because it's taught us what's possible when we're prepared, when telescopes are ready, when spacecraft can be redirected, when scientists have time to coordinate and instruments have the capability to capture details that matter. The next interstellar visitor might be detected by the Vera Rubin Observatory, a survey telescope that will scan the sky every few nights looking for anything that moves or changes. When it finds something, when that object turns out to be from beyond our solar system, we'll know what to do. We'll have protocols, we'll have experience, we'll have the lessons of 3I Atlas to guide our response, and we'll have the images, the sharpest ever taken of an interstellar comet, the result of years of engineering, months of planning, weeks of frustration, and finally the transparency that allows science to function. When those images appear next week, they'll mark a turning point, not just in the story of this specific comet, but in the broader narrative of how we study the galaxy beyond our immediate reach. They'll prove that even with limited resources, even with spacecraft designed for other purposes, even with bureaucratic obstacles and governmental shutdowns, we can still capture something extraordinary. We can still learn. We can still see what shouldn't be seeable and understand what shouldn't be knowable. That's the promise waiting in those unreleased files. Not just pictures of a comet, but proof that when curiosity collides with capability, when institutions remember their responsibility to share what they discover, when people demand transparency and scientists insist on access, remarkable things happen. The data gets released, the images appear, the waiting ends, and the next chapter of interstellar science begins. So where do we go from here? The HiRISE images are coming. That's not speculation anymore. It's confirmed by sources inside NASA, anticipated by the scientific community, and expected by everyone who's been following this story since October. When they appear, likely within the next week, they'll trigger a wave of analysis, discussion and interpretation that will dominate astronomy news for days. But the story of 3I Atlas doesn't end with those images. It continues as long as the comet remains observable, as long as telescopes can track its motion, as long as there's light reflecting off its nucleus and gas streaming from its surface. Right now, in mid-November, 3I Atlas is visible from the southern hemisphere. Observers in South America, Southern Africa, Australia and New Zealand can photograph it in the pre-dawn sky, watching its tail stretch across the darkness as it moves away from the sun. That tail is evidence of ongoing activity. The comet is still producing gas and dust, still responding to solar heat even as it climbs outward. That's important. It means the nucleus didn't evaporate during perihelion. It survived. Whether it survived intact, whether the solid core remained whole or fragmented into pieces, is still being determined, but survival itself is confirmed. Ground-based observations will continue through December. Professional observatories with large telescopes can track the comet's brightness, monitor changes in its activity, and measure the composition of gas in its coma. Those observations complement the HiRISE images. They show what happened after the Mars flyby, after perihelion, after the most intense phase of solar heating. By comparing pre-perihelion images from Mars with post-perihelion observations from Earth, scientists can reconstruct the comet's experience, how much mass it lost, how its activity evolved, whether its structure changed. The James Webb Space Telescope is scheduled to observe 3I Atlas. Again in December, Webb spectroscopy will provide updated chemical analysis, showing whether the comet's composition has changed as it moves away from the Sun. That might seem strange. Why would composition change? But comets can evolve. As surface ice sublimates, deeper layers become exposed. Those layers formed at different times, under different conditions, and might have different chemical signatures. By comparing Webb's earlier observations with its December data, researchers can track how the comet's outgassing evolves, what molecules are being released, and whether the activity is waning or holding steady. All of this data, HiRISE images, ground-based tracking, Webb spectroscopy, fits together like pieces of a puzzle. No single observation tells the complete story, but combined they create a comprehensive portrait of an interstellar visitor moving through our solar system, responding to our sun, behaving in ways that both confirm our models and challenge them. That's the beauty of this kind of research. It's collaborative, it's cumulative, it's built by scientists around the world, using different instruments, asking different questions, all contributing to a shared understanding. For those of us watching from outside the research community, the next few weeks offer something rare, a chance to see scientific discovery unfold in real time. The HiRISE images will appear. Analysis will begin immediately. Within days, preliminary interpretations will emerge. Not final answers, but informed assessments based on what the images reveal. Did HiRISE resolve the nucleus? What do the jets look like? How does the comet's appearance compare to earlier observations? These questions will be addressed quickly, not because scientists are rushing to conclusions, but because the community has been waiting for this data and is prepared to analyse it the moment it becomes available. Then, as December observations come in, the story will deepen, new data will refine earlier interpretations. Questions raised by the HiRISE images will be answered, or at least constrained, by follow-up observations, and gradually, over weeks and months, the portrait of 3I Atlas will sharpen. We'll know more about its size, its structure, its composition, its behaviour. We'll understand how it survived perihelion, whether it's typical or unusual among interstellar comets, and what its presence tells us about the population of objects drifting between stars. But eventually, the observations will end. 3I Atlas is moving away. Its brightness is fading. Its distance from Earth is increasing. By early next year, it will be too faint for most ground-based telescopes. Only the largest observatories will be able to track it, and even they will struggle as the comet dims further. Eventually it will become invisible, not because it's stopped existing, but because it's too far away, too faint, too small for our instruments to detect. At that point, 3I Atlas will return to the darkness it came from, travelling outward into interstellar space, never to be seen again. That finality adds weight to the observations we're making now. This is our only chance. The comet won't return. It won't loop back toward the sun like periodic comets do. Its trajectory is hyperbolic. It's passing through once, and once is all we get. That makes every image, every spectrum, every measurement irreplaceable. What we capture now is what we'll have forever. The data we collect will be analysed for years, referenced in textbooks, cited in papers, used as a benchmark for understanding the interstellar objects that follow. But the object itself, gone. A memory. A set of numbers and images preserved in archives. So when the HiRISE images appear, when NASA finally releases what should have been public weeks ago, take a moment to appreciate what you're seeing. Not just a comet, not just a scientific dataset, but a glimpse of something that came from another star system, that travelled for longer than human civilization has existed, that passed through our solar neighbourhood and gave us one brief opportunity to understand it. We're living through that opportunity right now, and in a few days, when those images go live, we'll see the culmination of engineering, planning and persistence, a moment when bureaucratic barriers fell, transparency prevailed, and humanity got to see what we've been waiting for.